going to do is there's a section in our, or a chapter in our book called R, and it's a review is what it stands for. Some of it's review for you. Some of you, it may not be review for you because depending on where you went to high school, if you had a class that covered some of this stuff. But the first section that we're going to talk about is the section on sets. And a set is just a collection of objects. When I was a kid, I collected sets of baseball cards. Now I have lots of baseball cards that are worth nothing. Nobody does that anymore, hardly. Unless you've got some really rare cards. And I just got it for the bubble gum. So sets are collections of objects. We're going to deal with numbers mostly in here. An element is a piece inside of a set. Okay, there's a notation, a Greek letter epsilon, lowercase epsilon. It's like a C with a little one line in the middle of it. So it's like you make the lowercase C, and then you put a line in the middle of it. That's the Greek letter epsilon, the lowercase version of it. That means an element of. So we'll see that as we go through some stuff here that we're going to use that notation out of that. Sets use set braces. And you'll hear me probably call these curly braces. Curly braces is what I usually say, but they're set braces is the real word for that. But it's curly braces is what you'll hear me say. So set braces. And then an example of a set would be, we'll call it set S. And it's just a set of numbers, 1, 2, 5, and 7. Doesn't necessarily have to have any kind of rhyme or reason to what's in the set. At this point, it's just a set. It's a group of numbers inside of curly braces. That's all that is. Now, inside of that set, there are elements. 1, 2, 5, and 7 are all elements of that set. That's kind of taking our definitions that we've done here and putting it to an example. So 1, 2, 5, and 7 are elements of that set. So we could say that 2 is an element of S. And that's the quote, how you would say that. 2 is an element of S. That's what this statement up here says. 2 epsilon S means 2 is an element of S. That's how you would read that. 2 is an element of S. 3, is 3 an element of S? No. So when we want to say something is not an element of S, we just take that same statement and then put a slash through the epsilon. That says 3 is not an element of S. That's what that says when you slash through there. It's like if you want to say something's not equal to it, you put a slash through the equal sign. Something's not equal. So not an element, just put a slash through the element symbol. Okay? All right. So there's a couple of different kinds of sets that we're going to deal with in this section. One is called a finite set. Finite. Finite set. A finite set means it is has a limited number of elements. One thing that you can remember with finite sets is you can count the pieces in a finite set. The number of people in this room is a finite set. We can count how many people are in this room. That's a finite set. Okay? The opposite of a finite set is an infinite set. It's unending or unlimited. number of elements. An unending or unlimited number of elements in that. Infinite set would be like all the numbers in the world. You think you've got to the highest one? Add one. It never ends. Okay? So an infinite set is unending. It has an unlimited number of elements. A finite set has a limited number of elements. You can count how many are in there. Okay? When you go a little deeper in set theory, there's a thing called a countable infinite set, but it's still an infinite set. So it has all the properties of an infinite set, meaning it doesn't end. It's unlimited in how many elements are in there. So finite sets are a set number. Infinite sets, not a set number. That's what you got to keep the difference in those two out of there. All right. So let's look at some sets of numbers that we deal with in this course and define them as finite or infinite. Okay. So the first set of numbers is the natural numbers. This is the first set of numbers that you learn as you're a kid. You know, I've got two boys. One's 5 and one is about to be 3. And the first set of numbers that you learn are the natural numbers. And they're called the natural numbers because it's natural how you count with them. The natural numbers are the numbers 1, 2, 3, 4, and keep going like that. That's natural, the natural way of counting. So the natural numbers, their abbreviation is a capital N, but you put like 2 bars on the slant. That's the abbreviation we can use for natural numbers. The N with the 2 bars. 1, 2, 3, 4, ... Keep going forever. The natural numbers. Are the natural numbers an infinite or a finite set? There's an end. They're infinite because you could keep counting forever, right? You can keep counting, past, get to 100. Well, 101, 102. Keep going. So they're an infinite set. So keep that in mind that they're an infinite set. Put that in parentheses beside it. The natural numbers are an infinite set. Okay. Let's look at this set of numbers. This is not a particular named set. We'll just call it, a set 1, 1/2, 1/4, 1/8. That set, we'll call that set A. Is set A finite or infinite? And what clue can we use to determine that? Is it finite? What's happening to our numbers here? 1 to get to 1/2, what are we doing? Dividing by 2, right? Half of a 1/2 is a 4th, half of a 4th is an 8th. The next number would be 16th. The next one would be 32nd, a 64th, 128th. Keep going. We can keep going. We get a smaller and smaller number, but it keeps going. Here's the clue. The ... at the end tells you, oh, that keeps going forever. That pattern that they've developed keeps going on forever. So that would mean that if it keeps going on forever, that means it doesn't end, right? So that would be what kind of set? Infinite set, because it continues forever. The ... is the clue there. Yeah. That is exactly correct. Yes, sir. Absolutely. So this would be an infinite set. We'll call that example A. Example B, let's look at a set. Let's call this set B. And maybe there is a pattern. And there is a ... But then they put a number at the end. What does that imply about that set? That it's got an end, right? Yeah, that ... in the middle says, okay, they've established a pattern. They started at 7, went to 8, 9. We know that ... represents which numbers? 10 through 14, right? Because the pattern has been established and it stops at 15. So this would be what kind of set? finite, yeah, because it stops. And it's got a certain number of elements in it because it ends. All right. Now, here's a weird way for them to set up a set. Let's say they had X and then this straight up and down bar. So that says X is what we're looking at. X is the number. The straight up and down bar is read such that, and then we have 9 is less than or equal to X is less than or equal to 13. Okay? That's telling me that X is what? Bigger than 9, smaller than 13. That's exactly what it's saying. That it's all the X's that are between 9 and 13. Okay? Now, would that be a finite or an infinite set? Finite. We got an ending place and a beginning place, right? So that's what indicates finite on that one. Okay. Let's look at some descriptions of sets, and then we're going to list the elements in those sets. List the elements in each set. So if we're going to list the elements, we're probably dealing with what kind of sets? Finite. If it were infinite, could we list them all? Definitely not. We could list some of them and establish a pattern, but we could not list them all. So let's look. We're on example D here. Here's our set X such that X is a natural number less than 7. So they've described the set in curly braces with words, and that's okay to do. I mean, it's still describing some numbers. It says it's a natural number, so we know the natural numbers are what kind? What are the natural numbers? 1, 2. Is 1/2 a natural number? No, that's not how my 3-year-old counts. He counts 1, 2, 3, that sort of way. That's the natural way of counting. So that's what the natural numbers are. Let's list those elements. What natural numbers are less than 7? 1 through 6. True. Integers would be the negative numbers involved. If we said integers, then the negative numbers are involved. Natural numbers are starting at 1 and going up. Whole numbers adds the 0 to it. And then integers adds the negatives to it. So we'll get into all those number sets very soon with that. Here, we're just kind of trying to describe what's going on in the set. So here we have all the elements of that set described in words. We've got it in number form. Okay. All right. That's easy to do. Nothing to that. Let's do one more of those. Curly braces X such that X is a natural number greater than 7 and less than 14. So what's the first number in that set? 8. It's a natural number that's greater than 7. So that's 8, 9, 10, 11, 12, 13. Is 14 included here? No, because it says less than 14. If it had said less than or equal to 14, then we include the 14. It just says less than. We have those 6 elements in that particular set. All right. So they describe a set in words. We're supposed to write the elements that are involved with that. It's really, you're dealing with finite sets. Just read it, understand, okay, that's natural numbers. That means no negatives, no fractions, no decimals. It's the numbers I count with, that sort of thing. Okay. All right. So let's go to kind of the next little thing, and some a little bit of definition stuff here. The universal set, same section. The universal set. If we're talking about a universal set, we're talking about all the things that are in the discussion. So everything in a discussion. And in math, that discussion is a problem. So like on the previous two problems, the universal set was the natural numbers because that's the big set of numbers that we were talking about. The description narrowed it down to those 6 elements, but the universal set was the natural numbers because that's everything that was in the problem. Okay, so universal set, everything that's in discussion, and then the null set, NULL, the null set, that's another name for the empty set. Handwriting's not, it's kind of dying off here. The empty set. If something's empty, how many elements does it have? None. Yeah, there's nothing in it. No elements. You'll see that depicted as an empty set of curly braces, just with nothing in it at all, no blanks, no anything. Empty set of braces, or sometimes you'll see the book note that with a circle with a slash through it. Both of those mean the null set or empty set. They kind of bounce back and forth which one they use. They mean the same thing. Okay. All right. Empty set, null set. All right. Then we have what's called a subset. A subset is a smaller group of elements from a larger set. Sometimes that larger set is the universal set. Sometimes that larger set is maybe just a larger set of numbers. Like you had 10 numbers and you have a subset of these certain 3, something like that. That's a subset of that. We're going to get some notation stuff as we go along here with some examples using these things. Okay, so example E, or this is example F. Sorry, example F. If A is this set, numbers 1 through 8. I'm just abbreviating there. Finite set, obviously, from 1 to 8. Okay. B is this set, 2, 5, and 7. We want to answer this question. Is B a subset of A? So to be a subset, that means every element in the smaller set has to be in the larger set. 2, 5, and 7 in set A. Yes. So B is a subset of A. The notation that we would use to state that is you'd use the letter B for the subset, and then this is the symbol for subset. It's like it's not a C, it's more like a sideways U with a line underneath it. Subset of A. And you would read that B is a subset of A. That's the notation that you might see with that. B is a subset of A. Let's look at another example there. Example G. Here's set A. Again, the numbers 1 through 8. Set C, 10, 15, 18. Is C a subset of A? C a subset of A? No. So we could write that with notation. C is not a subset of A. So if I want something to not be, what do I put through it? Slash it. Yeah, slash through there. C is not a subset of A. That's what that notation says. On a side note, the empty set or the null set, the null / empty set is not a subset of any set. Okay? So if that comes up or they ask you, is the empty set a subset of something? How can an empty set be a subset? It can't be. Okay, so that makes a little bit of sense there that you cannot have an empty set being the subset. Okay? All right. Next thing with sets in this particular section is the use of Venn diagrams. Does anybody remember using Venn diagrams? It's kind of a lost art. They don't use them as much as they used. Venn diagrams, that's the things with the circles and the football shape in the middle, where you have a set A and a set B. And then this part in the middle here is where A and B, it's the intersection of A and B. So you would have things that are only in A, things that are only in B, and then that football shaped area in the middle are the things that are in A and B both. Okay. So it's the intersection of those two. All right. So Venn diagrams, you can get more complex with them, have 3 circles. I've seen them with 4 and 5 circles. The more circles, the more complex it gets, but the more exclusive that intersection area is, because you got to be pretty special to be in all of the sets. Okay. So let's look at an example and put it into a Venn diagram. Letter H here. Set A has these elements: 3, 5, 7, 9, 11, and 13. Set B, 6, 8, 10, 11, 13, and 14. Not really a pattern established on that set B, but it doesn't matter. Let's build a Venn diagram for that particular, those 2 sets. So I'm going to draw 2 circles with the overlap. This is going to be letter A. This is going to be set B. What numbers would go inside the intersection? 13 would. What else? 11. Those are the 2 numbers that are in both sets. Over here on the left side, we need all the rest of the numbers that are in A. 3, 5, 7, 9. And then over here on the right-hand side, we want all the rest of the numbers that are in B. Okay? So 6, 8, 10, and 14. So there we have a Venn diagram based off of 2 sets out of that. Now, the intersection, the notation for intersection. This is, getting a lot of notation. Intersection. It's an upside down U. Okay. A intersects B with these 2 elements, 11 and 13. That's what that is showing in that Venn diagram, is the intersection of set A and B. Yes, sir.
If we had written this down, would it be marked wrong if the universal wasn't on the outside of the Venn?
What do you mean?
The universal.
like a box around it. No.
Okay, so
We're not going to be that picky
okay,
in here.
Let's go there and marking wrong with the universal.
If we're given a universal in the original problem, then possibly. Here, I didn't give you a universal to start with, so I wouldn't be able to say anything. Like, if you were given, technically, yes, if you were given a universal set, then technically, yes, it should be there. But here we weren't given one, so it wouldn't be. I'm not as picky as most guys are, probably. You may not think I'm laid back once we get going in the semester, but I'm as laid back as I can get, I guess. All right. The complement to an intersection is the union. So the union is the complete list of the elements in both sets. So if we're going to union two sets, and let's just say we use these same two sets that we had here in example H, the union of those two sets, A union B, is the list of all the elements that combine there. Don't repeat elements, though. If you got things that are in the intersection, only put those down once. So we have 3, 5, 6, 7, 8, 9, 10, 11, 13, and 14. That's the union of those two. Okay. Union makes sense, the U shape on the union out of that. Okay. Unions, and kind of a note here, union is in A or B. An intersection is more exclusive. In A and B. It's tougher to be an and than it is to be an or. Think about, the roads here. An intersection of two roads is a small spot, right? So an intersection is a smaller set than a union would be. Okay, an intersection is a smaller set than a union. I won't say in all cases, but most cases. Okay, so let's take a couple of sets and write out those unions and intersections just to make sure we got that, and then we'll go on to complements and fun stuff. So IJ. All right, so set W, just some random numbers here, 9, 15, 25, and 36. Set X, 15, 20, 25, 30, and 35. And that's fine. The first thing, let's find W intersect X. Where do those two intersect one another? 15, 25. That's it. There's two elements in the intersection. The union of those two, much bigger set, right? Because it's put it all together. 9, 15, 20, 25, 30, 35, and 36. Much bigger set on the union and the intersection. Do a real quick example here of an exceptional thing. Set G, 1, 3, and 5. Set H, 2, 4, and 6. Brace. G intersect H. Is there any intersection? It's the empty set. It's empty. There's nothing there. So the empty set. Or you could write the circle with a slash through it. Either of those is Absolutely fine with me on that. Know that they mean the same thing. So if you see on a multiple choice test, you don't see the circle with the slash through it, but you do see the curly braces that have nothing in them, they mean the same. Nothing crazy about that. All right. Little other definition here. The complement, not compliment like I like your shirt, but complement like math complement. The complement of a set. It's the elements that do not belong to a set. Normally from a universal set. Or larger set. Out of, that we're dealing with a larger set of numbers out of that. So example L, we'll call the universal set U, and we'll just put this be the universal set. 1, 2, 3, 4, 5, 6, 7. That's our universal set. So that's the only numbers that are in our discussion are that. And we'll call set A 1, 3, 5, and 7. This is what a complement is. The way you know to complement is with what's called A prime. So it's just like an apostrophe type mark there. It's kind of like what that is. It's read A prime. It means the complement. So that means the things that are in the universal set that are not in A. So 1, 3, 5, and 7 are in A. What are the parts of the universal set that are not in A? Yeah, 2, 4, and 6. That's the complement. Very simple. Okay. Complement of a set. All right. I'll make a note here on page 6 of your textbook. There's a tan box on set operations. It's just a good summary of everything that we've just talked about. Okay, so it's just all in one page there. There's a set operations box. So just know that that's there as a good resource for you to have out of that. So that's section R1. Let's go ahead and do R2, and then we'll get into actually some math, and then we'll take a short break and then come back. Okay. R2, we're going to talk about real numbers and their properties. I actually do some math in this section, some multiplying, adding, subtracting, all that stuff. Okay. All right. Now, when we're talking about real numbers, we're talking about the number system, not just real numbers like they exist. Real numbers as in the real number system. There's a larger set of numbers than the real number system. It's this huge box that's called the complex numbers. Complex numbers, though, that's the big set of numbers that we deal with in math classes. Complex numbers. Complex numbers involve the imaginary numbers. You remember in high school algebra, maybe you took the square root of -1. That's where I came from. That's where the complex numbers exist. Complex numbers are the i's and things. So like I, 2i, -3i, that sort of stuff. Those are complex. Those are imaginary numbers. The complex numbers takes those imaginary numbers and pairs them up with a real number. And that real number is a smaller box inside of this one. Okay, so and I didn't get it inside of there, so I'm gonna get it inside. There we go. That box is the real numbers. The real numbers are inside of the complex numbers. Okay, the real numbers have boxes inside of them. So inside of the real number box is another box. It's called the rational numbers. So if a rational number, if a number is inside the rational number box, that means it's a rational number. It's also a real number, but it's also part of the complex number system. So when you're further inside of the boxes you are, the more things you're part of. Okay? So it's boxes inside of boxes. So if you put something on the innermost box, it's really inside of all the boxes around it. Okay? All right, so rational numbers. Rational numbers are numbers like 1/2, 2/3. Numbers that can be written as fractions. That's what rational numbers are. The first 5 letters of rational are ratio. So ratio, normally in a math class, you'd write it as a fraction. So that's where rational numbers, ratios, they're fractions involved there. There's another box just outside of that. It's called the irrational numbers. So it just borders right up against that. It takes up this space inside of the real number box, but it's not inside of the rational number box. It's irrational. That means it's not written as a fraction. The irrational numbers are numbers like the square root of 3, the square root of 2, square root of 7, square root of 6, just numbers like that. That if you took the square root of those numbers, those decimals never repeat and never terminate. So that's what makes them irrational, is they could not be written as fractions. Rational numbers, remember, can be written as fractions, like 3/4, -7/9, 0.75. Same thing as 3/4. Anything that can be written as a fraction is a rational number. Inside of that rational number box is another box, and it's the integers. And Michael brought this up earlier. Integer. What about negative numbers? That's where the integers come in. The integers pull in the negative numbers, but integers are not fractions. They can be written as fractions, but they're not normally written as fractions. Integers would be numbers like -6. You could write that as a fraction because you could put -6/1, right? That makes it a fraction. So that means a -6 is a rational number, but it's also an integer because the integer box is inside of rational numbers. Okay? -6, -10, -11. All of those are examples of integers that are also rational numbers. They're also real numbers. They're also complex numbers out of that. Inside of the integer box, there's a lot of boxes. That's okay. We'll make it. Is the whole numbers. The whole numbers have 0 in them. Okay? Here's the thing about a whole number. A whole number is also an integer. Right? Because 0, -1, -2, keep going, toward the negative numbers, you've got integers. The whole number adds the 0. Inside of the whole number box, this is the last box that we have, is the natural number box. So that first section dealt with natural numbers a lot. The natural numbers are the beginning of everything. That's the regular numbers, 1, 2, 3, counting. That's the natural numbers. So if you're a natural number, you're also a whole number. You're also an integer. You're also a rational number. And you're also a real number. And you're also a complex number. So the further inside of this box you get, the more things you are. Okay? So if it fits in this box, then it really fits in all of the boxes. Okay? That's what we got. We're going to classify some numbers in this section. So this box picture is kind of a big deal. There's one in your textbook. I can't remember what page it's on, but there's one in your textbook that does this. It's the same picture. They just have, shading in their boxes and all that stuff. I think this does the job, okay? So let's look at a set of numbers. Example A, let's look at a set. I'm just going to put some numbers in this set. -8, -6, -12/4, -3/4, 0, 3/8, 1/2, 1, square root of 2, square root of 5, and the number 6. It's a finite set of just random numbers that I picked. No real pattern or rhyme or reason on a lot. There's a reason, but no real thing going on constantly there. Okay? Now, we're going to list the sets of natural numbers and I'm going to put the abbreviation out here beside of it so that you can kind of tie those together. The natural numbers. What elements in set A are natural numbers? So if you're a natural number, that means you're a counting number. And you can only be positive, right? Because we don't count, our kids don't count negative numbers starting off, right? 1 and 6 are the only two, right? 1 and 6. Whole numbers, and the abbreviation for whole numbers, it's a W, like a block W, and that left-hand thing is double lines on the left-hand side there. It's hard to do without doing it to begin with. There we go. Like that. W for whole numbers. Now, remember whole numbers, it's the counting numbers. So it's if you're a natural number, you have to be a whole number. What else does the whole numbers add? 0. And 0 is an element of A. So our set is 0, 1, and 6. Natural numbers, smaller set than whole numbers. Makes sense, right? Whole numbers, take the natural numbers and add 0 to them. The next set is the integers. And don't jump ahead on the abbreviation. It's not an I. It's a Z with a double bar in the middle. Why a Z? Ask those old Greek people that came up with this stuff. They used a Z instead of an I. I think it's because the I was kind of already had Roman numeral type implications on it, and it wasn't really easily discernible for them. So, integers. What does the integers add to things? The negatives. So, which ones are part of the integer set? -8, -6, -12/4. Why is that an integer? Because it reduces, right? To be what? -3. It's technically -3. They've got it written in disguise as a fraction, but it's really -3. But if you're an integer, you're also or you're a whole number, you're also part of the integers group, right? So you got 0, 1, and 6 in there as well. We'll see how our boxes are filling up more as we get outside of that smallest box, the rational or the natural numbers. As we start building out here, we got to the integers and our list is getting longer. Let's get to the rational numbers. The abbreviation for rational numbers is not an R. It's a Q with a little slash through it like that. Reason it's a Q is because rational numbers are written as fractions. Fractions mean what operation? Division. The word for division in math class is quotient. That's where the Q comes from. I do know the reason for that one. So if you're a rational number, that means you can be written as a fraction. So that would be adding which ones to the integer set? It'd still be there because it's written as a fraction. Negative 3/4 is a fraction. 3/8 is a fraction. 1/2 is a fraction. But technically, square root of 2 is not a fraction. It's a decimal that never ends, so it can't be written as a fraction. So all of these are still fractions too. We could write all of those as fractions, right? Just put them over 1. That one's already a fraction. It's just negative 3. So these are part of that rational number set too. So we've got -8, -6, -12/4, -3/4, 0, 3/8, 1/2, 1, and 6. The rational numbers picked up a lot of our stuff. The irrational numbers would be the what of the rational numbers. Okay, what word was it that we used? Started with a C. The complement of the rational number. So it'd be Q prime is complement of the irrationals, of the rationals. Complement of the rationals is the irrationals. So that would be square root of 2, square root of 5 in the curly braces. So we've classified those numbers by looking at the set of the elements in that larger set. Which one do they fit into? And the boxes, nested boxes is what you're going to, like those nested, what are the Russian nesting dolls? Is that what it's called? Where you got really big one, you open it up, there's one that looks just like it inside, and you just keep going, and there's more and more inside there. That's the idea with the number system, is that you've got this really big box, and the inside of that are smaller boxes that have certain kinds of numbers in them. Okay? All right. Enough set theory. Let's do some math. Same section. Let's do order of operations. Everybody's done order of operations. Order of operations, they're the law of the land when it comes to math problems. If you don't follow order of operations, you will not get the same answer as everybody else. We had to establish some sort of hierarchy of things. What is the order of operations? What always comes first? Parentheses. And when they say parentheses, they mean grouping symbols. A bracket's the same thing as a parenthesis. Technically, an absolute value mark is the same thing as a parenthesis. It's a grouping symbol, but we use parentheses as a generic term for that. Next would be exponents. And then what? Multiplication and division. Last, addition and subtraction. Now, keep in mind as you're doing these that you're doing parentheses, exponents, multiplication, division, addition, subtraction in what order? If there's more than one of any of them. First one, left to right. So left to, don't forget left to right. Left to right. If there's any like multiple things happening. So parentheses, exponents, multiplication and division, those happen together. Don't think you do not do all the multiplication and then go back and do the division. It's order left to right. Multiplication, division are ranked the same level. Addition, subtraction the same way. It's left to right. And that's where most people get mixed up with this, is not doing it in the correct order or doing all the multiplication and then going back and doing division. You've got to do multiplication, division together, left to right. Addition, subtraction together, left to right. out of that. I learned it, please excuse my dear Aunt Sally. I don't know how y'all learned it. That's the way I learned it. There's other words. There's a crazy geometry teacher at our school that does something weird. I can't even remember her saying, but she does something different. But it doesn't matter as long as you know that. Parentheses, exponents, multiplication, division, addition, subtraction. As long as you know that, I don't care which way you learned it. Just get it. All right. Let's look at some problems. Example B. Let's evaluate. 4 to the third power. Something boring, just a little exponent problem. What does it mean to have 4 to the third power? 4 times 4 times 4. That's what it means. Just multiply them together. 4 times 4 times 4 be 64. I'm not against you using a calculator. With the graphing calculator, I'm going to kind of show as we go along here how to do things with that. Exponents, 4 raised to the third power. To get the third power, over here underneath the clear button, there's a little caret symbol. It looks like a little house top. And that raises it into the exponents. And hit enter. And there you go. Cranks it out. Or you could type out 4 times 4 times 4 and get it to work. I just want to show you some things because not everybody's used graphing calculators coming up through math classes. I was lucky enough to get to use them when I was in high school, but not everybody did. Some schools are anti-calculator, which is fine. I'm kind of anti-calculator sometimes. But once we get here, I don't care. All right, -6 squared. That negative on the inside is important because that means we're multiplying what times itself? -6 times another -6, which would be positive 36. In the graphing calculator, it is very important that those parentheses be there. If I put -6 in parentheses and then square it, the squared button is over here on the left, I get positive 36. If I don't put the parentheses and do that, it gets me -36, which is not correct. It is very important that if you're squaring a negative number that you put it in parentheses. The way the calculator reads that is perfect order of operations. It says, oh, the exponent was on the 6. So it did exponents first and did 6 times 6 is 36. And then it said, oh, then it's multiplying by a negative. And it got -36. So it does the order of operations perfectly the way it's supposed to be done. Not the way you intended for it to do it, but that's the way the calculator reads it. It's a machine. It doesn't know anything except for what you type into. It's not intuitive as far as knowing what you meant. It just knows what you did. Okay, so be careful of that. Very careful of that. So many people miss problems on the first quiz, the first test, because they didn't type it in the calculator correctly. -4 to the fourth. So here's one that the negative, there are no parentheses. So it really is the way I typed that last problem into the calculator. It's 4 to the fourth power and then put a negative on the end. -4 raised to the fourth. 256. -256. I'm not asking you to do any of this stuff by hand. My Algebra 1 class at the high school hates me right now because I'm not letting them use a calculator, and that's okay. They're freshmen. They'll get over it. 14 years old. They'll be fine. Not traumatizing any of them, I don't believe. They'll get a calculator soon enough. So here, the parentheses matter. We have a negative number raised to the 6th power. So it's a negative number to an even power. So we know it should be positive just from some number sense. But if you can type it in just like it's written, you can get the right answer. 4,096. Of course, I don't know that off the top of my head. It's nice to know. Okay, so exponents, I go over those 4 examples there because it is important to know that if you're going to type these in the calculator, those parentheses are muy importante. in doing that. You've got to type them in there or not type them in there on purpose. You've got to be purposeful in how you're doing that. All right, so let's do some order of operations problems now that are just evaluate these. Just simple order of operations problems. 4 times 3 squared plus 6 times 4. Simple order of operations problems, but somehow they trip us up. Nope. Times. Sorry. Dot. I'll try to be intentional on a minus sign, make it plenty long. Now that, thank you for asking. I'm been at it for 13 hours today. I'm a little tired. That's okay. So what happens first? 4 times 3. So the first step would be 12, and then we're squaring that, and 6 times 4. 6 times 4. So which one happens first, the 12 squaring or the 6 times 4? Technically, the 12 squaring. Is it going to screw it up if you say 6 times 4? No, it's not, because it's separated by the addition. As long as we add last, we should be okay here. That's 144 plus 24, which is 168. That's doing it all by hand without touching the calculator, and that's okay. That's wonderful. Understand that you can just do this. 4 times 3, close parentheses, squared, plus 6 times 4. If you can type it in like it's written, it can get you the answer. Okay? So don't shy away from that. I try to say don't automatically jump to that. Number sense is something that will help you as you go through this course. So try to do some of it without a calculator if you can. But by all means, when it comes to things that are for a grade, check them if you're not sure. If you're sure, then great, go on. But if you're not sure, don't let your pride make you make a bad grade. What's a good book say? Pride goes before a fall. Is that right? 6 divided by 3 plus 2 to the third power times 5. Technically, what should happen first? The exponent, 2 to the third. So which would be 8. And then which one happens next? 6 divided by 3, technically left to right, 6 divided by 3 is going to go first, and then 8 times 5, and then the addition happens last there, which is 42. And again, you can, with the graphing calculator, it's not going to put that division symbol in there. It's going to put a slash, but it's 6 divided by 3 plus 2 raised to the third. If you're going to type that in, when you hit that raised to the third, it's going to be up in the exponent area. To get out of the exponent area, you got to press the right arrow key, and then times times 5, and then hit enter, and there you get your 42. Same answer out of that. So just trying to show you a few things that are unique to the graphing calculator that may not be, like some of the other calculators you may have used over the course of your life. All right. Example H. Excuse me. 4 plus 3 squared over 6 minus 5 times 3. So throwing a few negative numbers in here with this to do a little bit of work there. What's the difference in this problem and this problem? Nope. There's no difference. That one and that one are exactly the same. You do it in exactly the same order. So it's like you do the top part, do the bottom part, and divide last. That's the order that you would. It's an implied grouping when it's written like a fraction like that. It's kind of an implied grouping symbol that they just don't write usually. So I would do 4 plus 3 squared. 3 squared happens first. So that's 4 plus 9. Then on the bottom, I can kind of do that separately. 5 times 3 would happen next. So it'd be 6 minus 15. And then do the top part's 13, the bottom part 6 minus 15, be negative 9. And then reduce that if it will. It won't. If you did type this into the calculator, that's where the parentheses would have to exist. That's why I put that up there. That if I'm going to type this into the calculator to check it out, I've got to do the top part in parentheses, 4 plus 3 squared, divided by, then parentheses around the bottom part, 6 minus 5 times 3. My calculator is set to give me decimal answers first. I don't want decimal answers. I want a fraction answer. So to turn things into a fraction with the graphing calculator, you hit the math button and then enter twice. There's our negative 13 over 9. Math, enter on the graphing calculator to get answers that are in decimal in fraction form. You can set your graphing calculator to get you fractions automatically, but that's not always the best thing. Sometimes you do want them in decimal form. So I always just convert when I need to and go from there.
The calculator, I've never used it.
Mm-hmm.
I've only decided.
Yeah. They don't have a fraction button, but they do. Everything that mine's doing, they come standard with. Like everything I've done so far is exactly how one straight out of the store does it. You don't have to add anything to it. We shouldn't have to do anything special to any of them if you guys bring in an 84. 84, we should all be okay. It still does all of the operation stuff exactly the same. Everything's the same there. It's the statistic stuff that we will do later on. We're getting a line of best fit. It does that a little bit differently. It still will calculate it the same way and use the same algorithms to do it, but how you get it to do it is a little bit different, but not much. I'll show you that. It's not a big deal. Okay. All right. So let's go to some evaluating for x equals -2, y equals 5, and z equals -3. So we're getting some variables and some values for those particular variables. And if we're going to evaluate some problems, maybe it looks something like this: -4x squared minus 7y plus 4z. Something kind of, got an x, a y, and a z. We know what the number is for those. So what do we do with them? Just plug them in, replace, substitute, and work it out. -4 times -2 squared, 7 times 5. And I always, when I replace those, parentheses, always, just out of habit. If you make that a habit, you won't have problems. Extra parentheses don't cause problems. Lack of parentheses do. That's kind of the way I've always looked at that. So then you just work it out with order of operations. Whether you want to use the calculator or not, it's still order of operations to do that. So -2 squared is 4. 4 times -4 is -16. 7 times 5 is 35. 4 times -3 would be -12. So we're putting all those together. -16 and -35 would be -51. Minus 12 would be -63. And you can obviously type that directly into the calculator, from that step and get the exact same answer out of that. So I'm just trying to, go over a few of the nuances that you might have. 2 parentheses x minus 5 squared plus 4y over z plus 4. A little bit more complicated looking problem, but as far as difficulty, it's not any different. It's just put it together, plug in the stuff and work it out. So 2, and then the x is -2, so -2 minus 5 squared plus 4 times 5, and then -3 plus 4. Well, that works out nice on the bottom because -3 plus 4 is 1, so I'm dividing by 1, so technically I'm not even dividing by anything. Negative 2 minus 5 is negative 7 squared, and then I know that's 20. So negative 7 squared is 49 times 2 plus 20. Well, if it's 50 times 2, that's 100. But I'm subtracting, I'm only using 49, so that's 1 less each time. That's 98. Plus 20 is 118. Again, you can go into the calculator and do this. The key, if you're going to type it in, like at this step that's in red, make sure you put the top in parentheses and the bottom in parentheses, to do that. If you don't, it's not going to get you the same answer. Or you could just work the top with the calculator, work the bottom with the calculator, and then do your division. Just whatever works for you, whatever makes it work for you is fine. Okay. So evaluating expressions with the variables, just plug in the numbers and work from there. Really easy stuff. Okay. All right. Let's look at one last thing in this section, and then we'll take a short break and come back and finish up the last couple of sections for tonight. So the last thing in this section is simplifying an expression. Name of the game, like terms. If you're going to be like terms, then you're going to have the same variable and the same exponent on that variable, or not have a variable at all. So regular numbers are like terms for one another. Simplifying an expression would be something like, I don't know what letter I'm on, K. Example K, we might have something like 6 plus parentheses 9 plus x. We don't have anything in front of those parentheses like to multiply by. We're just separating the 6 and the 9 plus x with that parenthesis. But what are the like terms here? 6 and 9, they're regular numbers, right? So they're going to go together. What is 6 plus 9? 17. And then the x is just hanging out. He doesn't have any like terms, so he's just got to watch. It's like, okay, I'm just going to go along. 15, not 17. Thank you. Long time since 5 o'clock. Thank you. JKL. What if we had 7 minus 2 plus 3x plus 6 squared plus 5x? So throw in some order of operations in there and some simplifying. Mixing it all together here. What should technically happen first? The exponents, that's 6 squared. It's 36. Yes, I know we could put some other stuff together. What's 7 minus 2? 5. And now we can put like terms together. What goes with this 5 that's in front? The 36. There's a like terms. 5 plus 36 would be 41. And then 3x plus 5x, 8x. And it's positive, so it's plus 8x. And we would have our like terms put together there. The two strenuous there. Say we had 10y minus 6 minus 8y. Pretty simple there. Yeah, we got 10y and 8y, so that'd be 2y, and then the minus 6 is just hanging on. Nothing exciting happening with him. Like terms, putting the ones that are alike together. Nothing really strenuous about that. Okay. All right. That is